So yeah, we're doing cube root of 128. And so our function is x to the 1/3, cube root of x. And we know that for our linearization method for approximating, we need to have the derivative also. So what's the derivative of x to the 1/3?
1/3 x to the negative 2/3.
Exactly, which we will sometimes write as this 1/3x to the positive 2/3. So I'll just put it both ways. And then the value that we're trying to find is for 128. So we want x to be 128, and we need a, remember we call that the center of approximation. It's the number that's pretty close to 128 that we know the cube root of. So what's that number going to be, you think?
125.
125 seems like a good one since we know that the cube root of 125 is 5. All right, spectacular. So off to a good start. So we can say then that the cube root of 128 is f of 128, right? Which is approximately equal to the linearization at 128. And the linearization at 128 ought to be f of a. So that'll be the cube root of 125 plus f prime of a. So that'll be 1/3 times 125 to the 2/3 times x minus a. Everybody good with our setup? That's our linearization formula from before. F of a plus f prime of a times x minus a. And if you ever forget what that formula is, you can always just take point slope form and sort of adjust it into it. Any issues there or no?
Nope.
All right. So cube root of 125, like we said before, is 5. And then here, 125 to the 2/3. So that's the cube root of 125, which is 5, squared, which is 25. So we're going to have plus 1/3 times 25 times 3. So we're going to end up with 3's will cancel, 5 plus 1/25. 1/25, if I wanted to write that as a decimal, would be 5.04. Good or no?
Good.
Good.
Hold on 1 second. I'll be right back. Sorry. I just heard like all this screaming coming from my 7-year-old's laptop on their Zoom meeting. And I guess some person was like screaming and yelling in the background of one of the kids who'd forgotten to turn their microphone off. It was hilarious. What's up, Max? Now you're just gonna stand there and look at me. All right, go back to your class, dude. It was pretty funny. They were like screaming about how rude they were and they couldn't believe how they were doing it. It was funny. All right. Sorry.
Dang, overreact much.
Yeah. All right. Let's see. So somebody just sent me a thing in the chat asking me if I could do one with natural log. Yeah, I could. So I mean, I know there was one with the natural log on the homework assignment where I don't know what I asked you to find, the natural log of what, like 2 point something probably.
It was 2.
Mistaken.
Sorry, it was what?
2.8.
2.8. Okay. Let's see. Let's see if we can find an approximation for the natural log of let's the value I want to use here? How about the natural log of 5? No, that's no good. How about the natural log of
5.5.
I was thinking that, but I don't want to do that. Because then I realized that my math was wrong in my head. Now I have to like try to let's say the natural log of 7. I don't know if that'd be close enough. All right, we want to find the natural log of 7. So we're going to approximate this. And so we know, first off, that the function we're going to use is natural log of x, and that the derivative of that ought to be f prime of x, which is 1 over x, right? And our x value is going to be 7, but we got to figure out what our a value is going to be. Any idea what that a value could be?
9 or 4.
Well, it's got to be something that we know the natural log of offhand.
So
Unless you know those values.
10 or 8. E.
Yeah, so e though is not very close to 7. Right? We know the
2e.
natural log of e is 1. Natural log of 2e is equal to 1 plus the natural log of 2, which is a little bit irritating. And 2e is really actually not all that close to 7. Like e is about 2.7, 2.78128 or something, or 2.71288128, I think. So like that's still 1.5 units away. So how about the natural log of e squared? Somebody tell me what e squared is. Just not the natural log of it, but what e squared is.
5 point something.
No, e squared is not 5 point something.
7.4 is 7.35.
7.35. Okay, cool. Yeah, I was hoping it would be close enough. So 7.35.
Yeah, what's the exact value of e again?
The exact value of e is e. The decimal approximation, I believe, is 2.71288128.
Okay.
Something. So e squared, which is about 7.35, is pretty close to 7, and we can find the natural log of e squared because that's the same as 2 natural log of e, or just 2. So 2e, somebody said 5.5. That would have been a good value to look for if we were going to use 2e, because then we can use 1 plus natural log of 2. But natural log of e squared is good. That equals 2. That's pretty close to 7. It's about 7.35. So we'll use our center of approximation as e squared for that. Everybody good with that or no?
Good.
Okay, cool. So from there, we just need to say that we want, and I'm not going to write all that other stuff out this time. I'm just going to say capital L of 7 ought to approximately be f of a, so natural log of e squared, plus f prime 1 over e squared, right? F prime of a, times x minus a, so 7 minus e squared. Good or no? Which should be natural log of e squared, as we said, is 2, and then plus 7 minus e squared over e squared. And if we wanted to, we could make that all have a common denominator of e squared. So just to get this to look a little simpler, this could become 2e squared plus 7 minus e squared, so that'd just be e squared plus 7 over e squared. And what does that approximately equal?
One plus 7 over e squared, which is a bit less than 2.
Right, but what is that decimal approximation? Give me the like 5 or 6 decimals, please.
1.6109.
6109. Okay.
4.
And 6109 what?
4.
61094. Okay. All right. And what is, according to your calculator, what is the natural log of 7?
One 1.9459.
Ooh, really?
For the e squared plus 7 over e squared, I got 1.947, not 1.61, whatever.
Somebody else get 1.9 whatever also?
I think I made a mistake in my calculations on the calculator.
Okay. All right. I'll change that one in a second. So when we approximated just natural log of 7, what does the calculator say that is?
94591.
94591 and so on. Okay. And then, all right, what is this other number that we got here for e squared plus 7 over e squared?
94734.
94734. So on. Yeah. So we could see that's pretty close. It's off by a little less than 2 1,000ths, right? So pretty good approximation. DM, I know that's you asked for a natural log. Was that help?
Yeah.
Okay, cool. Everybody feel okay about this linearization stuff these days now? We're good here?
Yeah.
All right. Any questions on linearization? Because we're going to move on to something that's similar to linearization, but not quite exactly the same. All right. So we're going to still use this same idea that the tangent line is a very good approximation for the function to look at just other functions in general. And so when we do this, it's called using differentials, and it's really no different than using a derivative. What we're going to do is we're going to just say, well, if we look at these two different notations for the derivative, dy dx and f prime of x, they both just mean the derivative of a function with respect to x. They're really equal to each other. And if we think about what dy dx really means in terms of like slope, let's say, dy means a small change in the y value, right? And dx means a small change in the x value, right? That's what slope is, right? It's a change in y over the change in x. And if we're looking at this on a very small interval, the change in y is going to be a very small value, and the change in x is going to be a very small value. And if we treat each of those as if they were different variables, we could take the dx and multiply it over to the right-hand side to get this thing dy equals f prime of x dx, which is called it's not called the differential formula, but that's just called a differential right there. And basically what that's saying is you can take any function and on a small scale, you can say that the change in y dy is equal to the derivative of the function times the change in x. And it's only an approximation, but it's a very good approximation because we're using a tangent line to approximate it. It's about as good as all those other approximations that we got when we were doing the linearization. They're going to be off by 1,000th or 100th or something like that from what the actual change would be. But usually it's a lot easier to evaluate that approximate change on a derivative rather than the original function, because oftentimes original function might be complicated, but its derivative will be a little easier to evaluate. And so we're using that same idea that the tangent line is a good approximation for the function on a small interval. Does that make sense? Or no?
Kind of.
Kind of, okay. So basically you could think about it as if dy dx is slope, right? Change in y over change in x. And suppose, and we're going to look down here at this problem, we're going to have x go from 1 to 1.01. So when I do that, evaluating this at 1 is not so big a deal, but evaluating it at 1.01 is a little bit irritating. It takes some calculation. And then to find the change in y, we have to, see what the value was at 1 and see what the value was at 1.01 and subtract them, right, which would be a little bit annoying. But if we were to say the line tangent to this has a slope of 5x to the 4th plus 37, if I were to take that, the slope of that line, and multiply it by how much I went over in the x direction, dx, that should tell me how much approximately the function goes up in the y direction. Right, so the slope times the change in the x ought to equal the change in the y, right? And that, so if we think about it this way, slope is change in y over change in x, right? Well, if I take this and I multiply it by a small change in x, what does that do? It cancels out this change in x, right? And it just gives me a change in the y value. That's effectively what we're doing. We're taking a change in y over a change in x. That's our derivative, that's our slope. And multiplying it by a small change in x to see what the small change in y would be. Does that help or no?
Yeah, thank you.
Okay, so all you have to do is take the derivative of this and then multiply it by whatever your small change in x is. So that's what we got. We've got dy, the small change in y, is our derivative times the small change in x. And so dy ought to be 5 times 1 to the 4th plus 37, right? Because we started at an x value of 1. And then our dx is just 0.01. So 5 plus 37 is 42. And so 42 times 0.01 is 0.42. Good or no?
Good.
Will dx always be given to you?
Sorry, say that again?
Will dx always be given?
Yeah, I may ask you how much would x change if y changed a certain amount, so you might have to solve the other way around, but yeah, I'll give you some value for x and some value for dx. Or I might say like, oh, about how much does y change if x goes from 1 to 1.02, so then you'd have to at least be able to do that subtraction and say, all right, the dx is 0.02 because we're starting at 1 and going to 1.02.
Okay.
Does that make sense?
Yeah.
Yeah. Cool. All right. Any questions on that? All right. Let's see if we can do that for this one. Y equals sine 3x. And we're going to have x equals pi. And we're going to change by negative 0.02. So we want to know how much does the y value change on the function sine 3x if x goes from pi to pi minus 0.02. What should we do first?
Find the derivative of y.
Okay. So our dy should be, what's the derivative of sine 3x?
3 cosine 3x.
3 cosine 3x using the chain rule times our dx, our change in x. So our x is pi and our dx is negative 0.02. We just plug them in. 3 cosine 3 pi times negative 0.02. Good or no?
Good.
All right. So what's the cosine of 3 pi?
-1.
Should be -1. So that is 3 times -1 times -0.02, which is
3.02. Oh. Yeah.
Yeah, everybody good with that? So if the x value goes from pi to pi minus 0.02, the y value should go up by about 0.06. All right, let's do another one. This one's a little different here. We want to find the dy and evaluate it for the given values of x and dx. So we could solve for y, or we could treat this implicitly. And anytime I take the derivative of an x, I'll just call it a dx. And anytime I take the derivative of a y, I'll just call it dy for the change in x or for the change in y. So I think it's easier if we just take the derivative of x as dx, the derivative of y as dy, and then the derivative of x times y would have to use the product rule. So x times the derivative of y plus y times the derivative of x. And so now we will solve for dy because we want to find dy. So that will be dy minus x dy equals y dx minus dx. And we can factor out the dy over here and factor out the dx over here. If we want, we don't have to factor out the dx, but I'd rather have just one decimal over there to deal with than two. And dy ought to be dx times y minus 1 over 1 minus x. And we have a little bit of a problem here. What's the problem that we've got?
A y on the right side.
We got the y on the right side, yeah. And so how do we know what to plug in for the y? Doesn't seem like we were given a y value.
Solve for it from the original equation.
Yeah, so we'll just plug in 2 plus y equals 2 times y, gives us y equals
2.
y equals 2. So we'll plug those all in. We get dy equals dx times 2 minus 1 over 1 minus 2. And what does that give us? Negative 0.05. Any issues there? Are we good? I guess I'll take that as we're good. All right, let's take a circle that has a radius of 10, and we're going to increase that to a radius of 10.1. We want to use linearization to approximate the increase in the circle's area, if we did that. So what do we think? What should we do?
Something to do with the area or circumference of the circle.
All right, so we're talking about an increase in the circle's area. So let's write an
area.
equation for the area.
Okay.
Area ought to be pi r squared, right? And so we are interested in how much the circle's area changes, which would be a dA, a change in the area. So we'll take the derivative of pi r squared, which would be 2 pi r times the change in the radius. And so what value should we put in for r?
10.
And what value should we put in for dr?
0.1.
0.1. minus amount that the radius changes. So let's plug those in to find the approximate change in the area of this circle. 2 pi times 10 times 0.1, which tells us that that area is going to change by about 2 pi meters. And if there's units, make sure you don't forget the units. Good or no?
Good.
How did you go from the area of the circle equation to the dA equals 2 pi r dr?
This is just taking a derivative of both sides.
Oh, got it.
So the derivative of the area of a circle is its circumference?
That is correct. Yes. It's funny how those things work out. It's actually not, I guess, that funny. It's just the way math is. Like if you think about what's the volume of a sphere? Volume of a
4/3
sphere
pi r cubed.
4/3 pi r cubed. Well, what's the derivative of that?
4 pi r squared.
Which is surface area of a sphere.
Oh. Huh.
Math. What a crazy thing. Who'd have thought? It's kind of amazing, actually, how all this.
Yeah.
All right, everybody feel okay about the differential stuff here? It doesn't really get much more difficult than, you know, this one where we had to find the y, or this one where we had to write our own equation. That's about as difficult as a problem I'm going to give you for that. So.
Oh, wait, can you go over the rule again of like taking a derivative of it and multiplying it by the change of r?
Yeah, I mean, so that's what this whole idea of differentials is. It's the change in one variable is equal to the derivative of the function times the change in the other variable.
Yeah, all right.
You know, we want to do with this circle, so we said the area is pi r squared. We want to find the change in the area. So take the derivative of the area formula and multiply it by the change in the radius.
All right.
Does that help? Does that make sense?
Yeah.
Okay. All right. Let's see. Is this? I think that is Newton's method. All right. So before we move into talking about this thing called Newton's method, I want to draw a picture for you.
Oh no.
What? What's wrong with me drawing a picture? I mean, I am a horrible artist, but I'm not happy with that picture. I guess that's okay. All right, I'll accept that as my picture. So you seemed upset that I was going to draw a picture, somebody out there.
It's beautiful. Don't worry, it's beautiful.
Yeah, I mean, I'm a horrible artist, but oh well. This is a good enough picture. All right, let me ask you a really important question about this function that I've drawn here, f of x. Let me make sure that I've done a good thing here and labeled my axes. It's important to do that. Does this function f of x have an x-intercept?
Yes.
Yeah, it does, right? It's somewhere in there. Greater than 0 at least, right? Anybody have a guess of what that x-intercept is?
Wait, what's the function again?
It's y equals f of x. It's that one I drew right there.
Oh.
We don't know until you label the axis.
I did. It's an x-axis.
No, but with the interval.
No, I didn't do that.
Oh wait, I know the answer.
Okay.
The x-intercept of f of x.
Yep. What is that numerically? I'm looking for a numeric answer.
F of x equals
The
0.
Zero?
When
No,
f of
clearly.
x equals 0, it's x.
Oh, f of x equals 0. Yeah, that's true. But I want a numeric answer for the x value.
The numeric x-intercept of f of x.
Right. What is that number? I want the number. Looking for a number.
The
7,
number.
2, 3.1, 8,000 pi. I don't care. What is it?
1.
1. No, you are wrong. Good guess though. 1 was right here. I don't know how you missed that. I had that little mark there. See, that's 1. I didn't actually have that mark here. Here's 1. We guessed this was our x-intercept. Who was that? Who guessed that wrong?
Serena.
All right. Good job, Karina. Thank you for guessing that incorrectly.
Oh no,
Waiting.
it was Serena.
What? Oh, Serena.
Karina.
Serena. There's a Karina and a Serena. So wait, which one was it?
With
Serena.
an S.
S. Serena. Serena. Okay. Good job, Serena. You guessed wrong, but you at least were able to guess something, which is what I wanted. 1 was wrong. You were wrong. You were in fact horribly, horribly wrong, weren't you? Gosh, so wrong. You should be horribly embarrassed about that. Let's see. Now I have a question about this value here at 1, this x-intercept that you came up with, and we're just going to pretend that you didn't say 1. We're just going to pretend we guessed some random x-intercept and that it was wrong, which is all I really wanted somebody to do, was to guess a number and then for me to tell them they were wrong. Makes me feel smarter, you know, when I can tell people they're wrong. So does our function f of x have a value at, we'll say 1, at this value that we guessed to be our x-intercept? Does our function have a value at this x value?
Yes.
Yeah, it does, right? It's got a value up here. Let's just call this value here x sub 0 or x naught. Right, this was our first guess at the x-intercept. We're going to have to take a couple more guesses to actually get a good value for it. Okay. So we're going to call this x naught. What's this point up here? What are its coordinates? If the x coordinate is x naught, what's the y coordinate?
Why not?
Well, let's call it f of x naught. How about that? Same thing, but f of x naught. Yeah?
Yep.
Sure.
Okay. Now, let me ask you another important question about this function. At the point x naught, f of x naught, is there a tangent line to the function at that point?
Yes.
Yes. Could I draw that tangent line?
Yes.
I probably couldn't very well, but I could at least attempt to. Oh, nope, I can't.
Never mind.
Missed part of my line. There we go. I did it. All right. This is our tangent line. What's the slope of that line?
F of x naught, x prime over x prime.
No. What's the slope of a tangent line to any function? It's the derivative, right? What's the derivative of f of x?
F prime of x.
F prime of x, right? So we're going to say the slope is f prime of, well, what's the x value? The x value.
X prime.
F prime
or
of x,
x naught.
right?
Or
Because that's the x value where we took that tangent line. Slope of the tangent line is the derivative f prime, and then it's f prime of x naught. The x value is x naught. Would everybody agree that that's the slope of that tangent line?
yeah.
Yeah. Serena, you're good with that?
Yes.
Okay, just making sure you haven't like gone off to cry in the corner since you were so wrong with your x-intercept guess. You're good?
No, I'm doing okay.
You're emotionally stable? All right, good, okay. I was worried. All right, so let's see. Could I write the equation of that line? How do you write the equation of a line?
Point slope.
Point slope form, right? Point slope form is a good way.
Y minus
what?
y minus f of x naught equals f prime of x naught times x minus x naught.
Good. Everybody agree with that? Right, y minus the y value equals m slope times x minus the x value. Yeah or no?
Yeah.
Okay, cool. Now let me ask you a question about that tangent line. Does that tangent line have an x-intercept?
Yes.
Yeah, it does. Could I find that x-intercept?
Sure.
Yeah. Is this x-intercept closer to the actual x-intercept than Serena's initial horrible guess?
Yes.
Yeah, it is, right? This is a better guess. So let's find what this value is. This x-intercept should be, well, let's call it x1. It should be x1 comma 0, right? So the y value should be 0. And the x value will become x1. And if we're looking for x1, we should be able to solve for x1. 0 minus f of x naught is just negative f of x naught. So if we divide by f prime of x naught, that gives us negative f of x naught over f prime of x naught equals x1 minus x naught. And if we add the x sub 0, x naught over here, we would get x1 equals x naught minus f of x naught over f prime of x naught. Would everybody agree that that should be the value of x1?
Yes.
All right, cool. So this is still not a very good guess, though, is it? Still not a very good approximation for this x-intercept. But let's see. Well, does our function have a point at x1? Sure looks like it. Should have a point with coordinates of x1 comma f of x1. Yeah. And does our function have a tangent line at x1?
It does.
Oh, yeah, it does. If only I could draw it. There it is. We'll pretend that's good. And does our tangent line at x comma f of x1 have an x-intercept?
Yes, and it's closer
It
than
does, and it's closer.
whatever.
Still
That
kind of far away, but it's better, right? And do you think we could find, let's call that x2, do you think we could find the value of x2 by finding the slope of this tangent line to be f prime of x1 and then going through and doing this whole process again? What do you think x2 would be?
x1 minus f of x1 over f prime of x1.
Yeah, true. We could find x2 just by doing that. And oh, that's closer, but that's not real great still. Does our function have a value at x2? Sure looks like it. And our function has a tangent line at x2. And my goodness, that tangent line at x2 has an x-intercept. We could call that x3. We could probably find the value of x3. It'd probably be x2 minus f of x2 over f prime of x2. And then let's see. Oh, well, that's not that close. So we could maybe find the value of our function there, find the point, draw another tangent line, which would be even closer. And we could probably just like go ahead and repeat this process as many times as we wanted to until we were very, 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 very close to that x-intercept, to finding the actual value of it. Don't you think? Nobody thinks anything? Any of you still there?
Yes.
Oh, okay, good. Just making sure that people were still there. Does that make sense or no? We could continue this process over and over and over again until we had a really good approximation for an x-intercept. And we could approximate any x-intercept of any function that we wanted to without having to use a calculator, because we could do all this algebra on our own. To be a little bit of a pain. And we could get a very, very, very accurate representation of that x-intercept. Isn't that cool?
So cool.
So cool. It is. This is called, guess who came up with this? Newton, who was like smart or something. This is called Newton's method. Newton's method for approximating x-intercepts. And he just uses tangent lines over and over and over and over again. And you can imagine that if you were back in like, the age of Newton, when there was no calculator to just tell you what the x-intercept was, this would have been exceptionally helpful and very cool that you could just repeat this process a few times and get a very accurate representation of that x-intercept. And in fact, this is how your calculator approximates x-intercepts for you. It just repeats this process over and over and over again until it gets a very accurate decimal approximation of the x-intercept. Isn't that cool?
He was a smart man.
He was a smart man. Yeah, he was. Yeah, that's true. So we could probably convert these formulas, right? We maybe note that each of these, the next guess was always equal to the previous x value minus f of the previous x value over the derivative at the previous x value, right? x1 and then x naught, x naught, x naught, then x2, x1, 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 x3 would be x2, x2, and x2. So we could maybe write this as the next guess of our x-intercept is the previous x-intercept guess minus f of that previous x-intercept over f prime of that previous x-intercept. And so this, all of this is called Newton's method. And this is exactly what we just did. We took an initial guess. We used the tangent to the curve at that estimate to find another 0. And then we made that our new estimate. And then from that new estimate, we used the tangent to the curve again to find a new 0. And then we just repeated that over and over and over until we had an approximation to whatever number of decimals we wanted. Good or no?
Good.
Cool.
So does this go into like, do people use this to find irrational roots also?
Yep.
Oh, okay.
Yep, that is exactly what they do. Yep. And, I mean, it's used, this is how your calculator is programmed to find all of those different values that, if you plug into your calculator, what's the square root of 7? It basically does this to approximate it out to however many decimals your calculator screen will give you, right? Because finding, let's say, the square root of 7 is like finding an x-intercept of this equation, right? X squared minus 7. Its x-intercept would be at the square root of 7. So if you type in square root of 7 to your calculator, it says, well, what's the x-intercept of x squared minus 7? And it does it and finds it and tells you what it is. Good or no?
Good.
So like, for example, on your homework on this, I'm going to ask you to find like the cube root of 8. No, that's an easy one. The cube root of 9. Well, you'd use a function like x cubed minus 9, and you would just find the x-intercept of x cubed minus 9. Does that make sense?
Yep.
Cool. All right. So let's see if we can use Newton's method to find a solution to x cubed plus 3x plus 1 equals 0. Any thoughts on how we'll start? We need a first number to guess, right? Don't we? Serena, you want to guess a number for us again?
0.5.
0.5. Why are you choosing 0.5? Just out of curiosity. Any reason, or you just come up?
Because it's closer to 0 than 1.
Closer to 0. Okay. So you didn't want me to castigate.
Yeah, true.
All right. Let's think about this. We could probably come up with a better number than 0.5. also, and a number that's better than 1 to start with. X cubed plus 3x plus 1. If I plug in, if x equals 0, I get y equals 1, right? Or I get 1 equals 0, right? What if x equaled 1? Then y would be
5.
5. I guess I should have. How about x equals -1? Let's do that. That'd be -1 minus 3. -4 plus 1 is -3. And so where does it look like that x-intercept should be between? Since we went from a positive at 0 to a negative at -1, seems like that root should be between 0 and -1, right?
Yeah.
Yeah. So what we're going to do is we're going to just say, let's start with x sub 0 equals -0.5. And what's the formula we need to use? The next guess should be the previous guess minus the function at the previous guess divided by, well, let's see, what is f prime of x here? Should be 3x squared plus 3. So the derivative at the previous guess. This is the formula that you're going to use. And you're going to plug in -0.5 into this and get an answer. And then plug in your new answer into this and get a new answer. And then plug in that new answer and get another new answer until we have, how accurate do I want this? I want this to be accurate to either 9 or 10 decimal points. How long do you think that'll take?
A long time.
Perhaps a long time, yeah. So what I'm going to do is I'm going to have you grab your graphing calculator. I'm going to give you a little trick on how to do this a little more quickly and easily. So everybody have a graphing calculator with them?
Yep.
All right.
Nope.
My computer version of my TI-84 died on me a couple weeks ago. I don't know why, I just stopped working completely. So normally I would like share my screen on this and do it on the screen, but I can't. So what I'm going to do is I'm just going to explain to you what to type into your calculator. And if you have difficulty doing that, let me know and I can try to slow down and get you some help with it. But the first thing you need to do is just type in -0.5 and then hit enter. Don't do anything other than that. Just -0.5, enter. Have you all done that?
Yes.
All right, cool. So what that has done is it has saved your most previous answer to something on the calculator as -0.5. Now what you're going to do is you're going to type in this function over here, x sub n minus x sub n cubed plus 3x sub n plus 1 over 3x sub n squared plus 3. But anywhere it has an x sub n, you're going to replace it with the answer button, which I believe is second and then the negative sign. Is that right? Second negative sign is the answer button?
Yeah.
Yeah.
Okay, so here's exactly what you're going to type. Answer minus, and then since we're starting a fraction, we're going to open a parenthesis for the fraction. Then we're going to open another parenthesis for the numerator of the fraction. And anywhere you see the x sub n is still an answer. So you're going to say answer cubed plus 3 answer plus 1. Then you're going to close the parenthesis for the numerator, divided by new parenthesis for the denominator, 3 answer squared plus 3, end of parenthesis, and then end of another parenthesis for the entire fraction. And you're going to hit enter. When you hit enter, what do you get?
-0.333 a bunch of times.
-0.3 repeating. Great, okay. Now, don't touch anything else other than just hit enter again. And now what it's going to do is it's going to redo that same formula except with -0.3 repeating in it.
3.2 repeating.
You mean 0.32 repeating?
That's the one.
Okay, and just the 2 repeats, right, I believe?
Yes.
All right, hit enter again. This is your next x-intercept. Guess.
Point 322185355.
Okay, hit enter again.
One 1853546.
Okay, hit enter again. And I believe that one should probably come out to be exactly the same as x sub 4 was.
Yeah.
So once you come out to get 2 in a row that are exactly the same, you are at least to that number of decimal accuracy. So we are now at 10 decimal points of accuracy. And so we would say to the nearest, whatever that is, 10 decimals, the x-intercept of x cubed plus 3x plus 1 is negative 0.32218535546. And that's Newton's method. And your calculator does it really quickly for you, obviously, better than having to plug all those in by hand and evaluate them. And I think it's actually fairly amazing that by picking negative 1/2 as our first guess, within 1, 2, 3, 4 iterations of this, we are accurate to 10 decimal places just by using tangent lines, which is pretty darn good.
And so you can use technically any value for any starting value for x, and you just have to press enter enough times until you hit the same thing twice.
Generally so. Sometimes just due to the nature of the function, like if it has discontinuities or like vertical tangent lines and stuff like that in it, picking a number too far away might screw this up. But as a general rule, yes, you can pick a number further away. So like if you wanted to go back and redo this, but start at like x sub 0 is 3, you could go through and it'd probably take 5, maybe 6 iterations to get to 10 decimals of accuracy, but you'd still get the same value, which is pretty darn cool, I think. And that's Newton's method. Hooray!
Is there any way
Tomorrow-
to preset an equation into a calculator?
What's that again?
Is there any way to preset this equation into the calculator?
You mean the function, the x value minus the function over the derivative of the function?
The function, yeah.
Yeah, I mean, no, just because you have different functions every time. If I made this x cubed plus 4x plus 1, well, then this would have to be x sub n cubed plus 4x sub n plus 1 over 3x sub n squared plus 4. So like every function is just different. So no, there's not a way to do that, unfortunately. So we're going to stop there. We're going to do another 1 or 2 just for fun Newton's method problems tomorrow after we take the quiz, but I want to give you guys a few minutes to ask me any questions you might have had on any of the practice problems from yesterday. And you'll have the linearization differentials assignment that's due tonight. Doesn't have any Newton's method stuff on it, but I will post another Newton's method assignment that'll be due at the end of the day tomorrow. So does anybody have any questions on any of the functions that I put on that sheet to practice your maxima, minima, increasing, decreasing, points of inflection, concavity stuff? Did anybody even look at them, or did you all just say, quiz isn't until Wednesday, I'll wait till tomorrow?
I kind of did the latter.
I mean, if nobody has any questions, I'm happy to continue and do our other Newton's method problems today, but.
I do have a question on tonight's homework.
Okay, I can help out with that. What's the question on that?
So for number 5, I think, it was find the tangent of 0.8.
Okay.
And so I thought of using pi/4 because that's an easy value of tangent.
That seems like a reasonable value to use. So we'll have x equals 0.8 with a equal to pi over 4.
Right.
For those of you that don't submit your homework on time frequently, here's one of the problems from homework that we're going to have done right now. All right, so what was the issue you had there?
I'm just messing up somewhere in my algebra and I don't know where.
Okay. So if we want to approximate tangent of 0.8, we'll say that this should be the linearization at 0.8 is equal to our function at pi over 4, so tangent pi over 4, plus derivative of our function, so secant squared pi over 4, times 0.8 minus pi over 4. Did you have that?
Yes. And
Okay.
I substituted secant squared as 1 over cosine squared because I know that value.
Yeah, that's fine.
Right.
I can rewrite it that way on the next step here, if you'd like. So tangent pi over 4 is 1, and then so you change this to 1 over cosine squared pi over 4. So cosine of pi over 4 is root 2 over 2, so this is 1 over root 2 over 2 squared. Root 2 over 2 squared is 2 over 4, so this is 1 over 2 over 4, which if you take the reciprocal of 2 over 4 is 4 over 2, so 1 plus 2 times 0.8 minus pi over 4, which if you distribute all that through, looks like that becomes 1 plus 1.6 minus pi over 2, or 2.6 minus pi over 2. Does that make sense or no?
Yeah. Okay. I see where I messed up now. Thank you.
Yep, no problem.
So do you want us keeping it to not decimals? So just keep it as pi over 2.
Yeah, 2.6 minus pi over 2 is fine. If you wrote it out as the approximation, that's fine. Like if you put in your calculator, that's fine too. Yeah, either way, I don't really care.
Okay, cool.
Yeah. Okay, let's see. DM, I saw the message that you sent me, but I'm not sure what you mean. One that has an undetermined value in the function. I'm not sure what you mean by that.
For like finding maximums and minimums.
Oh, okay. Finding maximum, minimum. You want one that has like where the function is undefined or where the derivative is undefined?
I guess the function.
Okay, so something where the function itself is undefined. All right, let me think about that for just a second. Something where the function is undefined. How about, I don't know how.
Wait, I mean the derivative.
What?
I meant the derivative.
Oh, you want the derivative to be undefined. Okay, something where we have the derivative undefined. Okay. On that sheet, there must have been some where I had like the cube root of something times like x minus something, or 5 minus 2 cube roots of x, or something with like a cube root in it somewhere. Did I have any of those? Or like a 4th root or a square root?
Yeah.
All right, what's one of those? Read me off one of those.
Cube root x squared times 3 minus 2 times the cube root of x.
That ought to do it. Okay, that ought to have what you want in there, Jim. So, let's first off find the derivative. So to start off with that, easiest way is to probably just distribute the x to the 2/3 to both pieces of this. So this becomes 3x to the 2/3 and then minus 2. And if I do x to the 2/3 times x to the 1/3, I'm sorry, minus 2x, that just becomes 3x to the 2/3 minus 2x. Everybody okay with that? right? X to the 2/3 times X to the 1/3 is X, and then the minus 2X, and then 3X to the 2/3.
Yeah.
So now we'll take our derivative. So our derivative, this should become 3 times 2/3, which is 2. X to the negative 1/3, and then minus 2 as our derivative, which we could rewrite as 2 over the cube root of X minus 2. And so we would hopefully note that this y prime is undefined at x equals 0, right? Because I can't have a 0 in the denominator. And then y prime equals 0 if 2 over the cube root of x minus 2 equals 0, or if 2 over the cube root of x equals 2, which would tell me, since the numerator is here, 2 and 2 are the same, that the denominators would need to be the same also. So the cube root of x would need to be 1, or x would need to be 1. So we have two critical values, x equals 0 and x equals 1. Everybody good so far with that?
Yes.
Okay. So then we will plug in something less than 0. So plug in a negative number like negative 1,000. Cube root of negative 1,000 is negative 10, right? It's negative. So this first number is going to be negative. Minus 2 is still going to be negative. So the function should be decreasing. And then something between 0 and 1, like something easy for us to cube root would be an 1/8. Right, so the cube root of an 1/8 is a half, and 2 divided by half is 4. So 4 minus 2 is a positive. So we're then increasing. Then we'll plug in something greater than 1, like, I don't know, 8 is a pretty easy number to cube root, right? So plug in 8, cube root of 8 is 2, 2 over 2 is 1, minus the 2 is negative. So we end up decreasing negative infinity to 0 and 1 to infinity, and we end up increasing 0 to 1. And then to find the local min and the local max, we'd have to find f of 0, and f of 0 would be 0 times 3 minus 0, so that'd be 0. F of 1 would be 1 times 3 minus 2, so f of 1 would be 1. So we have a local min of 0 at 0. And a local max of 1. Everybody good so far with the first part of that?
And do you want us to like box our decreasing, increasing stuff, or will you find it?
I mean, sure, boxing it would be great.
Okay.
Yeah. And if I asked you where these occur, you'd have to say the local min of 0 at 0 and the local max of 1 at x equals 1. So then we need to find a second derivative. So we'll take the derivative of our first derivative, y double prime. So 2x to the negative 1/3 becomes negative 2/3 x to the negative 4/3. And the minus 2 becomes just a 0. So this is our second derivative, or negative 2 over 3x to the 4/3. And this never equals 0, but it is undefined at x equals 0. So we make a sign chart for 0, plug in a positive number. Positive to the 4/3 is positive, and then multiply by a negative 2/3 is negative. And if I take a negative number cube rooted is negative, and then to the 4th makes it positive. So I have a positive times this negative is still a negative. So we would say no points of inflection, and it's concave down for its entire domain. And you could say never concave up, but saying that it's concave down from negative infinity to infinity is probably good enough to state that there's no No intervals where it's concave. Any questions on that? Dan, is that sort of what you were looking for?
Yeah.
Cool. Any questions on that?
For points of inflection, you want the point, both the x and y value, correct?
That is correct. If there's a point of inflection, I want x and y value. Definitely. Any other questions?
And then just to jog my memory, with the increasing and decreasing, if there's a numerical value, sorry, a loud car went by. And if there's a numerical value, you want brackets on those numerical values.
As long as the point is defined on the function, yes. Correct.
Okay.
Yep. If the point is not defined on the function because of like an asymptote there or something, then still keep the increasing or decreasing intervals in parentheses. But normally that won't be the case. Normally they should be in brackets. Except the infinity values would be in parentheses. All right.